I will compare discrete and continuous case. On this board I'll do discrete case. And on this board I'll do continuous case. So in both cases we have a set of operations that form a group. So in discrete case we have and in continuous case numbers, which we can think of angles if you think of group. And the number of the parameters is the rank of the group. Now we describe the group by its multiplication table in a finite case, which in that case is called a regular representation of the group, but it's just a matrix which has zeros every place except for the unique element obtained by multiplying I and the inverse of Gj. Here, it won't be quite like that, because whenever you have a group, you really want to write it that is continuously generated. You have to bring parameters and matrices of the same dimension that the group has, if you're looking at the representation. And these guys are called, set of these matrices don't form a group, they form a Lie algebra. So the multiplication table for Lie algebras is not on the level of group elements, which are infinitely many, but on a level of generators group transformations, which are finitely few. So for example, for SO2 there is only one. Instead of this multiplication table, we have another relationship. Then the key idea in both cases, and as you'll see they're really the same, is the notion of averaging. So the average over the group is defined as taking some object that the group acts on. Vectors, it could be acting on functions defined over state space, some coordinates, and it could be acting with different representations. So having formally the same multiplication table, but acting on very different spaces. But the idea is just to elements and then normalize it in such a way that if whatever is just number 1, we get 1 back. So average over constant should be average. In continuous case, the group integral group elements. So in this case, it's a continuous integral. Now it looks a little bit fancy, but you know it for rotation group SO2. For example, this is just an integral over angle from 0 to 2 pi divided by 2 pi. So for a specific example, it's easy to work out. But actually, there is no need to work them out explicitly, because you will see, and that has a fancy name, this AA Haar measure. But hard measure just means you have to make sure that if you're integrating, for example, over a sphere, that this solid angle on the sphere and this solid angle on the sphere carry the same weight, so that it's uniform over the sphere. You could design very stupid measures in which everything that's on a pole, that you do when you do Mercator projections. So of all these great orthonormality relations, etc., is very simple. There are only two rules that define everything. Average of 1 over the group has to be 1. That constant back. Rule number 1. And then there is a rule number 2 that says if I take an average over a non-trivial vector, it has an index runs from 1 to dimension, and it will be dimension of the reducible representation. If I average over that, I get 0. The discrete group is 3 elements. Then I can take a vector in a plane, just to make it very simple. I can act on it rotation of group element that rotates by 1/3. I can act it with 2 rotation. And obviously the average over this vector of the space is 0, because it runs on a circle, so sum of these two things. So that'll be true for any n, and that's the idea between any. If you have something that's not affected by the action of the group, then it just returns the thing back. If it's smeared out by the action of the group, then it'll be smeared out to 0. And in case of the Haar measure, what happens is elements of the group, which means I'll act on all other vectors of that kind. If it's uniformly sphered over a sphere, I get 0. So it has to be in an irreducible representation. Non-trivial vector, that's the total content of the theory. In quantum mechanics, it's often called Schur's lemma. All these details are more torturous than necessary because content is very simple if you have an overview. But it's important to work out a number of examples before you appreciate the general theory. So it's a constant tension between teaching you stuff that you already know. So some pedagogy consists in assuming that when you teach quantum field theory, I should use the same notation as I used in ordinary quantum mechanics because you're familiar. I think that's totally wrong. I think you should teach every subject anew and then understand their units afterwards. Is all you need to know, but it was very painful for physicists to learn it, and it's still scattered over. Wigner and Eckert had to relearn it. This immense blowback from the old farts who simply will not do group theory. They call it group and pest. They all use group theory, just didn't like that it looked like mathematics. So Wigner couldn't publish.
I can't get no satisfaction, baby.